This presentation talks about the cardiac pacemaker. It will be presented by Catherine, Stephanie, David, Rayon, and Abigail. What is a pacemaker? A pacemaker is a small device that is placed in the chest or abdomen to help control abnormal heart rhythms. Basically, it uses electrical pulses to offset anything that's going wrong within the heart. It can correct fast, slow, or even irregular heartbeats. Now, how does the pacemaker actually work? Well, these electrical impulses begin from the actual pacemaker device and they travel from the top of the heart all the way to the bottom via the sinoatrial node, or the SA node. It's also important to understand that one heartbeat consists of the atria contracting, which pushes blood into the ventricles. When the ventricles contract, this pushes blood into the rest of the body. Now, what does a pacemaker look like inside the body? Well, it's placed in the upper left chest area, and then two leads go from the pacemaker into the heart. One is attached into the right atrium, and then the other lead is attached in the right ventricle. In addition, it is important to know that the power source of the pacemaker is a small battery that has actually a very long life. Now, this pacemaker works by sending an electrical pulse down through the two leads, and the combined electrical signal from both the heart and the leads corrects the heartbeat. You may be asking, why do we even need a pacemaker in the first place? Well, it can prevent fatigue, fainting, loss of blood, and even organ death. Because if the heart isn't beating properly, then it's not going to provide blood for the entire body, therefore resulting in any of these horrible circumstances.
The major components of a pacemaker include a signal processing array for the input from the heart, a pulse generator, and leads that transmit information to and from the heart. The signal processing includes a filtering stage, an amplifier, and a comparator. The circuitry determines whether or not the pulse generator needs to supply a signal to the heart. This is done by comparing the processed signal to a threshold voltage. If the signal is below threshold, the pulse generator sends pulses to the heart to cause contractions. It is important to note that these pulses must be long enough and have high enough amplitude to cause depolarization of the cardiac muscles.
The circuit in a pacemaker device consists of a battery which powers the device, a microprocessor, a sensing unit that amplifies the small electrical signal received from the heart, and a pulse generator that delivers electrical pulses down the lead to the heart. The electrodes on the pacing lead, which plug into the connection block of the pacemaker, have the ability to receive electrical energy, send this back to the pacemaker, and then to deliver a small electrical charge to the heart to make the heart beat if it is going too slowly. The passive lead of the fixation mechanism has tiny prongs to connect into the mesh of the cardiac tissue. The active fixed leads have a tiny corkscrew which bore into the cardiac tissue to secure itself. The way the pacemaker circuit works is that the cardiac signal is sensed by electrodes and is amplified by a low-noise preamplifier. It is then filtered by a second-order low-pass filter to get the appropriate electrocardiography. This signal is applied to the comparator, which is used as a threshold detector to detect the heartbeat and generates a pulse with every heartbeat. The external comparator consists of two inputs, the ECG and threshold voltage. It generates a pulse depending on the threshold voltage level. The output stage is called the charge pump, consists of a pulse generator to stimulate the heart. A high-voltage pulse is delivered to the heart through pacing electrodes that must be customized for each patient. The SVS is necessary to monitor battery voltage.
A basic two-transistor circuit is modified to function as a cardiac pacemaker. The two transistors are utilized because they provide a very high gain, which is necessary to overcome the high impedance between the two electrodes that are placed on the heart muscle. Since the main component of the pacemaker is placed just beneath the skin, a flashing neon light is used to indicate when the battery needs to be replaced, and is activated when the mutual inductance drops below a critical value. This circuit is very similar to the first pacemaker and is still commonly used today. Demand pacemakers differ from traditional pacemakers in that they take input from the heart and only turn on when the heartbeat is irregular. The timing circuit is responsive to cardiac activity and is able to activate the pacing function when the heartbeat is not within the standard norm. The sense amplifier allows the inhibition of the pacing pulse from the pacemaker only when the heart is beating on its own. This type of pacemaker is used when the type of heart disease is only intermittent.
Pacemakers also bring a few challenges to the table for both users and producers. They include both the size of the power source and the pacemaker, the reliability, infections, which can be caused by wires and surgeries that lead to allergies and rejection, pacemaker syndrome, the ethical issue faced whether or not pacemakers should be turned off by caregivers, and lastly, frequency and radiation wave interferences, and these are just a few to be named. Luckily, there are a few solutions to the challenges faced by pacemakers. New magnesium ion batteries are both smaller in size and can last for a great deal of time when compared to lithium ion batteries. Also, their charging time is much smaller than current batteries in lab tests. Proper wire and lead disinfection procedures must be followed by surgery staff to give a greater chance of acceptance by the body. Pacemaker syndrome is when the blood flow or pressure coming into the heart is not the same as when leaving the heart. Atrial or dual chamber pacing has known to help deal with this blood flow issue that are faced by 5% of pacemaker users. As newer components are being built with greater quality, passive and active filters have shown great results in dealing with interference so long as they are kept a few inches from the pacemaker.